Welcome everyone back to our course on memory device technology for AI/ML computing. I am Dr. Shubhadeep from IIT Hyderabad, your course instructor. So today we are going to begin with the fourth part of our sixth module on ENVMs. But before that, let's have a quick recap of what we had covered in the last class. So first we saw that there are several performance metrics in our RAMs, such as variability, endurance, retention, and multi-bit scalability. So the tunneling distance in HRS was a key factor affecting variability in our RAMs, whereas for endurance failures, creating a permanent filament due to hard dielectric breakdown was very important. We also saw how both these issues can be mitigated using pulse schemes and materials engineering. In the case of retention, the thermal dissolution of conductive filaments in low resistance state and diffusion of ionic species in the high resistance state were both causing a drift in resistance in these respective states as a function of time. Also, we looked at how having gradual IV characteristics can enable multi-bit operation with DC biasing, and furthermore, using very short pulses of hundreds of nanoseconds, you can gain access to multiple non-volatile resistance states. So this analog memory behavior, which has more than 100 states in a single device, may not be very good for digital applications due to signal to noise ratio, but they are excellent for analog computing for low power AI hardware. Also, we saw the issue of sneak paths, which was preventing the scaling of RRAMs into crossbar arrays, and how these were mitigated with array biasing and selector device configurations. In the final portion, we saw the commercialization efforts with lot of promising results, especially from startups like Crossbar and VBit Nano. We saw that while currently our RAMs are being primarily used for niche applications such as embedded, automotive, and also IoT applications, there is a great opportunity to be employed in hardware security and also for analog in-memory computing. So with this, we concluded our section on RRAMs, and today we are going to start with a very exciting section on magnetic random access memories. And this is a very significant change in approach to making memories or storage elements, because for the first time, we will move from just charge-based devices or even filamentary systems to look at magnetism. Magnetism is what will be used, or the spin degree of freedom is what will be used to store information in MRAM devices. So first and foremost, it is very important to delineate or clarify how MRAMs are different from your age-old magnetic tapes or magnetic disks. So in the magnetic tape or disk, you had a magnetic fill, and you basically store data by changing the magnetization of that magnetic fill. And in fact, this is the oldest form of non-volatile memory storage. However, please note that magnetic disks had these rotating, moving parts, and a read-write head was also a mechanical moving part, and this made data access sequential and very slow read and write access times. This was in the orders of hundreds of milliseconds. Therefore, they are not really what is very useful for ENVM application space or the storage class memories. For ENVMs, the first thing that you require is a random access memory, not sequential access. And also, you need to go completely solid state. Solid state means you cannot have any moving parts, and the control must only happen through electric fields, and that is going to be the focus of our study today. So before we go into MRAMs, let's look at the area from where MRAMs have come from. So the area from where MRAMs have come is called spintronics. So what does spintronics stand for? It is a amalgamation of the term spin and electronics. Till now, we have been only looking at charge-based devices. So the movement of charge or the trapping of charge or storage of charge was what was responsible for both the transport of information, the storing information, and also the manipulation of information. So now we will look at spintronic devices where in addition to the charge of the electron, the spin degree of freedom is also used. Okay, so let us try to understand what is spintronics by looking at three fundamental questions. So the first fundamental question is, what is spin? So as you may know from your basic physics, spin is the fundamental property of particles like electrons, protons, neutrons, and it is similar to charge or mass. Despite its name, we should recognize that there is no physical spinning. There is no physical spinning like that of a ball. But in fact, it is a quantum mechanical property which gives particles some kind of an intrinsic angular momentum. But the best way to kind of visualize what spin is to imagine that since the electron has both charge and spin, it behaves like a tiny magnet with a magnetic moment. And therefore, you can have both upspin and downspin of electrons. Important thing to know is that spin is such fundamental to particle physics that there are two subdivisions of fundamental particles named fermions and bosons, where fermions, what we are interested in, such as electrons, have half integral spin, bosons have integral spin. And spin forms the fourth quantum number or the spin quantum number. So as I just mentioned, the spin in electrons can be in the up direction or in the down direction. Sometimes it is also referred to as plus half and minus half. So next question we will try to ask is, how do you use spin? So in charge-based devices, the way we manipulate the flow of charges or storage of charges is using electric fields or electrostatic potential. However, in spin-based devices or to manipulate spin, we use magnetic fields, and this is the additional degree of freedom. Now, a little bit of physics understanding or at least the terminology is important to appreciate the manipulation of spins using magnetic fields. So the idea is that when a system is subjected to no magnetic field, there is spin degeneracy. So what is the meaning of spin degeneracy? Spin degeneracy refers to the condition where an electron has two possible spin states, the spin up and the spin down. And in the absence of magnetic fields, both the spin up and spin down states have the same energy, and therefore they are called degenerate. However, this degeneracy is lifted or broken when you subject the material to an external or applied magnetic field. And as you can see, the two states which were earlier degenerate become non-degenerate. That means there is a splitting in the energy level. And the magnitude of the splitting is directly proportional to the applied magnetic field. So minus half spin has higher energy than the plus half spin, and the delta E is equal to G multiplied by the Bohr magnetron multiplied by B. Let's not worry about what G is, but mu B is the constant of proportionality and it's a fundamental quantity. It is called the Bohr magnetron, and this value is very, very tiny. It is almost 5e minus 5 electron volt per Tesla. So for reasonable magnetic fields, the amount of split in the energy that you get in the plus half spin state and minus half spin state is in the order of few MeVs. And this is one of the primary challenges that spin-based systems face, whether it is for logic or it is for information storage, that the difference in the energy levels are so tiny, having good signal to noise ratio becomes a very big challenge. Nonetheless, why do we choose to use spin? That is a really interesting physical concept that we should look at. Now, you have to understand that all charge-based transport is inherently dissipative. What I mean is, suppose you apply a voltage on a material in plus x direction, the current also flows in the plus x direction. And as we have seen from our basic physics, the multiplication of current and voltage gives you the dissipative Joule heating. Okay. However, In spin currents, the situation is completely different. In spin currents, as you can see from this particular diagram, that the spin currents are orthogonal to the applied electric field and applied magnetic field. So here electric field was in the x direction, magnetic field, which may or may not have been applied, was in the z direction, and the spin currents happens to be in the y direction. Since the spin currents are orthogonal to the applied electric field, the product or the dot product is zero, and therefore the promise is that spintronic devices which use the spin degree of freedom will have much lower power consumption. So it is not absolutely dissipationless because there is a charge component also, but the promise at least is that spintronic devices will be much more power efficient compared to purely charge based devices. Okay, with this brief introduction, let us go to the first demonstration of utilizing spin in a practical device. And this was the Nobel Prize winning phenomena of giant magnetoresistance. So this phenomena of giant magnetoresistance, or GMR, was invented in 1988 independently by a French and a German scientist. The magnitude of the discovery, especially in technological aspects, was so large that in 2007 they won the Nobel Prize. So let us try to see what this GMR effect is. To understand GMR effect, first we have to understand the device stack in which they noticed the giant magnetoresistance. So the device stack consists of a non-magnetic metal sandwiched between two ferromagnetic metals. So what is a ferromagnetic metal? Ferromagnetic metals such as iron, cobalt, nickel and their alloys are metals where the tiny magnetic moments of the atoms from unpaired electron spins naturally align in one direction, creating a very strong magnetization. So the special property is that they stay magnetized without an external electric field, but lose this property above a certain temperature called the Curie temperature. So what the scientists Furt and Grunberg checked was, in such kind of structures which has a non-magnetic metal sandwiched between two ferromagnetic layers, is that they started checking the resistance across this device when it is subjected to an external magnetic field. So this is what happens in this particular device, where chromium is the non-magnetic material which is sandwiched between two layers of iron. And what they notice is that at zero magnetic field, the device is in a high resistance state. However, when you start increasing the magnetic field in either direction and you reach around 2 kilogauss, plus minus 2 kilogauss, the resistance drops quite significantly. And that is why they call it the giant magnetoresistance. Now, the fun part here is that if you look what is the change in resistance, it is only 1.5%. 1.5% difference between high resistance state and low resistance state seems very less for charge based devices, but for magnetoresistance based devices this is quite a significant number. So now we will try to understand, why does this device show high resistance at zero external magnetic field, but once you start applying an external magnetic field, the device goes into a low resistance state. And to understand this, the first thing that we need to recognize is, what are the directions of the magnetization, or the directions of majority spin in the two ferromagnetic layers at zero magnetic field and at a finite external magnetic field. So at zero external magnetic field, it turns out that the stable configuration in which the two ferromagnetic layers spin configuration or magnetization exists are opposite to each other, and this is called the anti-parallel configuration. So why is the stable configuration anti-parallel? Let us try to think from an example that you might have experienced in your childhood. In our childhood, we used to play with magnets. So let us assume we have a strong magnet whose this end is North Pole and this end is South Pole. Suppose you bring a weaker free moving magnet near this stronger magnet. What will be the most stable configuration? Of course, they will be anti-parallel in nature, because the North Pole of the free moving magnet will be attracted to the South Pole, and the South Pole of the free moving magnet will be attracted to the North Pole of the fixed magnet. That's why at B equal to 0 or at stable configuration, you have anti-parallel orientations in the spin or magnetization of the two ferromagnetic layers. Now what happens? You start applying an external magnetic field. When you start applying an external magnetic field, it is natural that if this top ferromagnetic layer is slightly weaker as compared to the bottom ferromagnetic layer, and you don't apply very high magnetic field such that even this changes, naturally the configuration of the free layer will flip. It will change because now the external magnetic field will try to align or try to influence your weaker ferromagnetic, which is free to flip its orientation. So at B equal to 0, the stable configuration is anti-parallel. At B not equal to 0, the stable configuration is parallel. So this is well understood, but still it does not answer the question, why is the resistance of this stack in anti-parallel configuration greater than that in the parallel configuration? And to understand that, we have to be familiar with a really complicated concept in quantum mechanics called spin-dependent scattering. Now, a full treatment of spin-dependent scattering requires you to understand exchange interactions, which are an integral part of spin systems when you give it a quantum mechanical treatment. But of course, that is not really necessary for this course. So I'm going to try to simplify things for you. So what we are going to imagine is, imagine that you have two magnets like this. Both are oriented with each other. What would you expect if two magnets are oriented in parallel configuration with each other? They will repel. Yeah. So this repel, you can imagine, is like more scattering. Now, if two tiny magnets, which are nothing but two electrons having same spin, interact with each other, they will cause more scattering, and therefore they will have high resistance, because more scattering results in higher resistance. However, if these are two small magnets which have opposite spin or in anti-parallel direction, you will see that the scattering will be much lesser, and therefore the resistance when these opposite spins interact with each other will also be lesser. So how does this help? This helps when we start looking at what happens through this particular configuration when you have parallel and anti-parallel spin configurations. So in this diagram, let's start with the anti-parallel spin configuration. In the anti-parallel spin configuration, the spin of ferromagnetic layer 1 is in the up direction, and that of ferromagnetic layer 2 is in the down direction. Now what do we do? To measure any resistance, what we do is we inject through this system something called the charge current. What is a charge current? A charge current is a current where there is no preferential spin orientation. So 50% of the electrons will have downspin, whereas other 50% electrons will have upspin. What will happen to the downspin? Just look at spin-dependent scattering. So the downspin will not see much scattering from the opposite spin configuration, but it will see lot of resistance in the same spin configuration. The exact opposite will be the case for the upspin. In ferromagnetic layer 1, it will have lot of scattering, because in ferromagnetic layer 1, the overall spin configuration is in up direction, but it will not have any scattering to the ferromagnetic layer 2. So if we have to draw equivalent circuit diagram, the downspin will have very low resistance in the first ferromagnetic layer, but high resistance in the second ferromagnetic layer where there is the same spin configuration, and exactly opposite will be the case with the up spin. High first in ferromagnetic layer 1 and low in the second ferromagnetic layer. Now let's see what happens when the same charge current is injected through this device when it is in parallel configuration. So when it is in parallel configuration, it is easy to understand. While the downspin will suffer no scattering or very little scattering, both in ferromagnetic layer 1 and 2, the electrons with upspin will suffer large number of scattering both in the ferromagnetic layer 1 and ferromagnetic layer 2, and this is what is represented through this equivalent circuit diagram. So in this equivalent circuit diagram, you see upspin has very little resistance, whereas downspin has very large resistance. You can do a very simple resistance analysis and show that the resistance of the parallel configuration will be lower than that of the anti-parallel configuration, and the reason is that here 50% of the spin sees only low resistance, whereas other 50% sees very high resistance, whereas in the anti-parallel configuration, both spin up and spin down see high resistance. Okay, so therefore the overall resistance experience by the device in parallel configuration is in low resistance state, whereas anti-parallel is high resistance state. Now correlate that with what we saw in B equal to 0. You are in anti-parallel state, therefore it is in high resistance, as you can see over here, whereas when B is not equal to 0 or B is greater than 0, you start seeing the low resistance state kick in. However, at this point, it should be noted that just like in the first demonstrations of giant magnetoresistance, the difference between the high resistance state, which was in the anti-parallel configuration, and the low resistance state, which was in the parallel configuration, is very, very tiny. Even doing a lot of significant engineering of the materials can only increase this number from 1.5% to, let's say, 10 to 15 or maximum 30% at room temperature. And this small number of 30% is not really enough to make useful devices. And therefore, people started moving from the phenomena of giant magnetoresistance to tunnel magnetoresistance. Now, what is tunnel magnetoresistance? Tunnel magnetoresistance is the phenomena that happens in a magnetic tunnel junction. So let me define what a magnetic tunnel junction is. As you can see in this figure, there is not much difference between a magnetic tunnel junction, which shows TMR, versus the device which was showing giant magnetoresistance. All you have done is you have replaced the non-magnetic metal which was sandwiched between the two ferromagnetic layers by a non-magnetic tunneling oxide. And this tunneling oxide is generally made very, very thin, 2 to 3 nanometers. And therefore, all this charge transport which was happening through only metallic layers, and therefore it had very low resistance, now you have a much higher resistance state because charge transport happens through tunneling through these layers. And a lot of engineering is done to figure out what are some good tunnel oxides. Earlier generations use aluminium oxide, but the current generations of magnetic tunnel junctions use magnesium oxide because it shows very good interfacial properties with most ferromagnetic metals. Now let's try to understand the operation of a magnetic tunnel junction, why the parallel configuration gives you low resistance state and the anti-parallel again gives you high resistance state, by looking at this simplified band structure diagram of a magnetic tunnel junction. So let us first consider the parallel state. In the parallel state, what happens is the majority spin both in ferromagnetic layer 1 and ferromagnetic layer 2 happens to be in the same direction. In the given example, both these are in the downward direction. So if tunneling has to happen from ferromagnetic layer 1 to ferromagnetic layer 2, two conditions have to be satisfied. The first condition is there should be enough states in the same spin configuration in the ferromagnetic layer 1, and there should also be enough empty states, that is the second condition, in the ferromagnetic layer 2. And as you can see from this diagram, both these conditions are met, so the tunneling probability is very high and lot of tunneling can happen. Therefore, this is in the low resistance state. However, if you look at the anti-parallel configuration, whereas ferromagnetic layer 1 has most of the spins oriented in the down direction, in ferromagnetic 2, most of the spins are in the up direction. And therefore, although there are a lot of states in the down direction available for tunneling, there aren't enough empty states in the down direction. And this is why, because of the Pauli's exclusion principle. Remember, what is the Pauli's exclusion principle? It is that electrons can only go from one state to the other state if they have the same quantum number. So therefore, spin has to be preserved when the tunneling has to happen. So it is not only enough for density of states on the left hand side ferromagnetic layer 1, but there should also be empty states in ferromagnetic layer 2. And because of the absence of empty states, this device in the anti-parallel configuration has low tunneling probability and therefore very high resistance. So with this understanding, let us see for practical technology why we moved from giant magnetoresistance to tunnel magnetoresistance. And the first reason is that the sensitivity of TMR devices is much larger compared to GMR devices, where TMR devices have almost 200% of sensitivity. GMR devices have very low sensitivity of 10 to 30%. Now, what is sensitivity? It is slightly modified version of your memory window, which is nothing but the ratio of high resistance state to low resistance state. In magnetoresistance percentage parlance, you say that the sensitivity is the difference between the anti-parallel state and the parallel state divided by the parallel state, which is the low resistance state. Furthermore, people saw that since there is a tunnel oxide in magnetic tunnel junctions, the leakage current is much lower compared to these structures. Therefore, there is much lower power consumption and better temperature stability in TMR devices when you compare it with GMR devices. Why is there better temperature stability? This is because the tunneling transport mechanism itself is very insensitive to temperature variations. The tunneling probability is not a strong function of temperature. Okay, so let us conclude our class over here. So in our class today, we looked at using the spin degree of freedom and how spin degree of freedom was used in practical devices. First using giant magnetoresistance and tunnel magnetoresistance, and without going into too much quantum mechanics, we try to understand what is the reason why parallel and anti-parallel configurations both in GMR and TMR have low and high resistance state respectively. Okay, so thank you for your attention. In the following class, we will look at translating TMR or magnetic tunnel junction devices into practically realizable technology. See you in the next class.